Hi everyone, welcome to today's topic. So this is topic number 20, and for topic number 20 I have chosen spinal. So this is an important terminology from coordination chemistry. So you have to have the idea about what is the structure of spinal, for which case or for which crystal structure we call it a spinal, and what are the types of spinal, and how can we define for a particular example what kind of spinal this is. Okay, so these kind of questions are actually asked in the exam, CSIR NET exam. So direct questions are coming from it. So that's why I have taken this topic. And I have previously told you that coordination chemistry and organometallic chemistry both are important chapters from inorganic chemistry. So let's start with today's topic, and I hope you will enjoy this session. So keep listening. First, what is a spinal? So this is a type of crystal solid. Okay, so type of crystal solid. Fine. Next is its general formula. It is very important, which is Ab2X4, where A is a di-positive cation, B is a tri-positive cation, and X is di-negative anion, like O, sulfur, oxygen, sulfur, not fluorine. Okay, any negative ion can be there, but generally we took oxygen or sulfur. Okay, so for a crystal means in the solid state we have read about the crystals, right? So in the class 12th also we have read the solid state. So we have some preliminary idea, right? So what are the type of unit cells? How many number of atoms are present in each unit cell? So that actually we know, that is known. So generally it happened from that chapter only, and BSc also we have read it. So for a crystal, generally what is happening is that the anions generally occupies the lattice points and makes the lattice. Lattice points means, let's say this is a simple cubic crystal or a cubic unit cell. So this is a cube. Let's say this is a cube. Okay, simple cubic crystal. Lattice points are these points. These are their lattice points, where by which actually the crystal structure actually formed. Okay, these points are called lattice points. So in lattice points actually occupied by the lattice points are occupied by negative ion. Okay, and which actually responsible for the making of the lattice or the structure of the lattice. And what about the cations or anions? So as they are very small in size, very smaller than anion, right? So that's why they actually occupies the holes, tetrahedral and octahedral. Fine. This is in general case we have read that for any crystal solid it is happening. Fine. So A here, uh, the thing is that here this A, which is a di-positive cation. So many kind of spinels are there. So I will be talking in the next slide, and A2 plus and B3 plus. These two kind of cations are there, and their ratio, please try to remember that their ratio is 1:2. Fine. So that is the case, and okay, fine, 1:2 and 4. Okay, 4 means here anion is 4, means in the lattice which is forming by the anion has Z equal to 4. Z means the number of atoms in each lattice, right? So Z is here 4. Okay, so and we know the formulas. The we have previously actually read about this in solid state. That's why I'm just putting this. I am trying to make you remember these things. So what is happened in the case of let's say for a lattice, or for a, yes, for a lattice, n is the or Z I have taken here. N is the number of atoms. Number of atoms per unit cell. Okay, for a lattice. Number of atoms per unit cell for a lattice. Unit cell. Okay, so uh, then the number of tetrahedral void or hole, tetrahedral void or hole will be equal to 2 into n. Okay, and number of octahedral void or hole will be n, which is equal to the number of atoms, and it is the tetrahedral void is twice of the number of atoms. Okay, these are some general idea, and octahedral void is okay, that is fine for now. Let's go to the next slide now. And okay, octahedral void is actually much smaller, the r, let's say radius, smaller than the tetrahedral void. Fine. Now next is the types of spinel. One is normal spinel, another one is inverse spinel. There are another kind of spinel which is mixed spinel. I will be talk about that also. And right now the more important thing is the normal and inverse. Okay, you have to find out what spinels are normal, what are inverse. Okay, now AB2X4 I have previously told you. Now A plus in normal, for the case of normal spinel we are showing. Okay, A plus will be in tetrahedral void. We know cations are actually occupying the voids, so A plus is occupying the tetrahedral voids. 2B3 plus, because it is in 1:2 ratio, 2B3 plus is there, so it will occupy the 2 tetrahedral void. 2 means here the 2 of B3 plus actually occupied the octahedral voids. Okay, and for the case of inverse spinel, what is happening? A2 plus will now go towards octahedral void, and 2B3 plus can occupy both octahedral and tetrahedral. So one among the two B3 plus or half of the B3 plus will occupy the octahedral void, and another half will occupy the tetrahedral void. Fine. So actually what is happening here? So if we write, this is 2 plus, right? This is 2 plus, this is 3 plus. Okay, so I am writing here A2 plus, B, let's say 3 plus and 3 plus, and X4. Okay, so here actually what is happening? Exchange of the A to B and B to A, right? So A is going towards inside or the octahedral void it is, and B is going out to the tetrahedral void. Okay, so there is an exchange of these two cations, okay, A and B. So when it happens, what will be there? In the tetrahedral, this is tetrahedral, and in the octahedral there are A2 plus and B3 plus. Fine. So this is in tetrahedral void, 1B plus. 1B plus is in octahedral void, and A2 plus is in octahedral void. Fine. Now coming to the normal spinel. Okay. So the spinel where the tri-positive ions occupy the octahedral void, right? We have previously told, na? I have previously told you where the tri-positive ions occupy the octahedral voids and the di-positive ions occupy the tetrahedral voids. This I have told you previously. So the condition, so to know that this spinel is a normal spinel, what we have to do? This because we cannot see the lattice from inside, right? Where the ions are actually sitting, and how their arrangement is, that we can't actually understand, right? By seeing a crystal or by seeing a lattice. So we have to somehow find out by seeing the their by seeing their cations, anions, the formula actually. Okay. So the condition one is the CFSE of B3 plus in octahedral field should be greater than CFSE of A2 plus in octahedral field. Okay. So we have to calculate the CFSE for both B3 plus and A2 plus in octahedral field. So if CFSE of B3 plus is in octahedral, so here what is happening? A is in tetrahedral, B3 plus is in octahedral, and X4 in lattice point. Okay. As B3 plus is in octahedral void, that means the CFSE of B3 plus in octahedral void should be greater than what? The A2 plus in octahedral void, so that exchange will not happen. So the higher CFSE means higher stability. CFSE higher means stability will be high, right? So in the case of B3 plus, the octahedral field, its CFSE must be higher than what? Then when after exchanging this A2 plus will go into the octahedral void, right? So that time CFSE will be less. Fine. For example, so this is the actual condition. One, we can do the other ways, but I will I prefer actually this only, the calculation of this. This will give you the correct answer. Okay. So for example, let's take Mn3O4. How can we write Mn3O4? Okay. Let's say like this, because it is a spinel, right? So you have to find out that it is a spinel. How can we find out? So three cations are there and four anions. So it can be a spinel. And the other condition is one cation should be in 2 plus and two cations should be in 3 plus oxidation state. Okay, or 3 plus state. So now you can see this is a spinel, right? So now what we have to find out? What we have to find out? We have to find out the CFSE for Mn3 plus, right? And in octahedral, and CFSE of Mn2 plus octahedral, right? That only we have to find out. So Mn means D5 system and Mn3 plus means this is D4. So and O2 minus, this ligand, this O2 minus, sorry, this ligand is sorry, O2 minus, this ligand is actually the weak field ligand, so it can't pair up the electrons. Okay, so we have to consider the higher spin arrangement only. So D4 means 1 2 3 and 4. Okay, so what is the CFSE for this? CFSE will be equal to what? See, this is what? 0.6 and this is 0.4, right? So 0.4 minus should be there. 0.4 into 3 plus 0.6 into 1. This will be your or 10 decay. So it will be equal to minus 1.2 plus 0.6. It will be minus 0.6 below. Fine. We know now the CFSE of this Mn3 plus, right? Now we have to calculate the CFSE for the Mn2 plus. Okay. So for Mn2 plus, we know this is a D5 system, right? And we have to, okay, I have to take the eraser. We can't take that. Okay, fine. So next what we have to do? Okay, now we can get it. Okay. Okay. So the CFSE for Mn2 plus octahedral. It is D5 system. So for D5, 1, 2, 3, 4, 5, as it will be high spin, right? This is 0.4. So we have to see the mod value only, okay? No positive and negative. The only mod value we should take. This will be 0.60, okay? And here it will be what? D5 we know, CFSE is 0. How? Minus 0.4 into 3 plus 2 into 0.6, which is equal to 0. So this is obviously less than this. So CFSE of Mn3 plus in octahedral field, the CFSE is greater than Mn2 plus in octahedral field. So it will be obviously what? Normal spinel. This is an example of normal spinel. Okay. Now coming to an inverse spinel. So we have previously told you that the exchange of cations are there. So A2 plus and B3 plus are there. B3 plus and B3 plus. Let's say O4 or X4. This will be exchanged with 1B. So what will happen? B3 plus tetrahedral and A2 plus and B3 plus is in octahedral and X4. Okay. Fine. This will happen in the case of inverse spinel. So spinel where half of the tripositive ions occupy the tetrahedral voids and the dipositive ion and the rest tripositive ion means B plus are occupying in the octahedral voids. That time we will call it inverse spinel. So condition, obviously the opposite condition should be there, that the CFSE for A2 plus in octahedral field should be greater than the CFSE for B3 plus in octahedral. Fine. For example, Fe3O4. Okay, when you are giving Fe3O4, you have to understand that it is a spinel, so it has 1, 2 plus and 1, 2, 3 plus ions. Okay, so now we will calculate it. Okay, here. So for the case of Fe2 plus, we don't know it is inverse or normal, right? We have just taken the general formula for spinel. Okay, this is the general formula. 2 plus should be in tetrahedral void and 3 plus should be in octahedral. When it is inverse, that time it is called inverse spinel. Okay, so it is the general formula of spinel only. So Fe3 plus in octahedral. Fe2 plus in octahedral, let's say I am calculating. This is D6 system, right? So 1, 2, 3, 4, 5 and 6. So CFSE will be minus 0.4 into 4 plus 0.6 into 2, which is equal to minus 1.6 plus 1.2. Means 0.4 minus 0.4 below, and we will take only mod value, so it will be 0.4 below. Fine. Now for Fe3 plus. Okay, so in octahedral obviously, and it is D5. So CFSE is for D5 system. What is the CFSE? CFSE of Fe3 plus will be 0, right? We have seen in the Mn2 plus case. Obviously for D5 system it will be 0 CFSE. So what is happening here? The CFSE of Fe2 plus in octahedral field is greater than Fe3 plus in octahedral field. So obviously it is the inverse spinel now. Inverse, right? Okay, so that is the case. And next is the few conditions for spinals. So I have seen various kind of examples of spinal, and I am here just giving you few points which will be needed or which will be helpful to study these spinals. Okay, so these are some few points I'll be talking about. So first condition is if both A2 plus and B3 plus are non-transition metal. Like for example, many cases you can have this kind of example like MgAl2O4, this kind of. So this is a case of metal, right? Metal 3O4 like structure, right? Spinal. So MgAl2O4. These kind of examples you can see, okay, for when you will practice. So if both A2 plus and B3 plus are non-transition metal, that time what will happen? Normal spinal, because it doesn't have any CFSE. Sometimes size factor is also considered here, but generally you remember this. Okay. Now second one is, the point is D3 and D8 has the highest CFSE among all. We know that, right? And they all prefer octahedral world. So to avoid more time consumption, when we see that D3 system is there, like what? Vanadium 2 plus or chromium 3 plus, like that, and D8 is nickel 2 plus, right? So this kind of system are when present, you have to consider it that it will be go inside the octahedral foil. Fine. Third one is if A2 plus is a non-transition metal and B3 plus is a transition metal having configuration D1, 2, 3, 4, not 5 is here, 6, 7, 8, 9, not 10 is there. Because D5 and D10 gives you the CFSE 0. Right? So that's why we are not considering that. So if A2 plus is a non-transition metal, means it can be lithium, magnesium, no lithium, magnesium can be there, right? Magnesium, any two positive cations, okay? And B3 plus is a transition metal having this kind of configuration, having any CFSE value, which will be not non-zero CFSE value. Okay, for that what will happen? Normal spinal, because A2 plus is a non-transition metal, it doesn't have any CFSE, right? A2 plus, and the inside B3 plus has some sort of CFSE, okay? It can be high, it can be low, right? But for every cases it will have the CFSE, so the exchange will not happen, okay? It will be normal spinal. The fourth case is if A2 plus is a transition metal, the opposite of 3, the case 3. If A2 plus is a transition metal and B3 plus is also a transition metal having configuration D0, D5, D10, means CFSE 0 cases. So inside the octahedral void, so A2 plus is now having CFSE, non-zero CFSE value, transition metal having non-zero CFSE value, and B3 plus has the transition metal but having configuration like that way where the CFSE is 0. That time what will happen? It will be obviously inverse spinal, because inside the octahedral void there is no CFSE, if it goes inside, it will gain some CFSE in octahedral field, right? So the exchange will happen. Now some examples. Okay, so here MgAl2O4. So both are non-transition metal. Right? So what will happen here? The normal spinel. Okay. The second case, ZnFe2O4. Okay. Zn2 plus, Fe3 plus. Okay. You have to consider it like that way. That it is given. Okay. Now both are transition metal. Fine. And CFSE of the outside, like CFSE of Zn is 0. Zn octahedral. 0, right? D10 system. And CFSE of CFSE of Fe3 plus is there, right? D5. D5, it will be also 0, right? So in these cases, if the CFSE of the both systems are 0, normally it will show you the normal spinel, because no gain of CFSE is there after exchanging, so it will show the normal spinel. Okay. Now FeCr2O4. Fe2 plus is outside, Cr2O4 is 3. Okay. So Fe2 plus D6 system in tetrahedral, but it is what? It will not a low spin kind of complex, right? Because oxygen 2 minus, O2 minus is a weak field ligand. So it will be the case. So the CFSE will be minus 0.4. Okay. You calculate it, you will find out the minus 0.4. We will only take the 0.14 for the comparison. And now Cr3 plus means D3 system. CFSE. CFSE is what? We know for the D3 and D8 system, the CFSE is the highest. Yes. So the CFSE of the Cr3 plus is 1, 2, 3 will be there, right? So if T2G and EG is there, EG and T2G, so 1, 2, 3, right? So it will be minus 0.4 into 3. It will be minus 1.2 daily. So obviously the CFSE of the tripositive ion in octahedral field is greater than the CFSE of dipositive ion in octahedral field. So it will be obviously normal spinel. Okay. There should be one driving force. Okay. So no driving force is there. Okay. Here is also both are 0. And here both are transition metal, not having any CFS. Fine. Now coming to mixed spinel. Okay, what is a mixed spinel? So mixed spinel is when CFSE of both dipositive ion and tripositive ion are 0, which we talked about actually previously. In this, for this case, I was saying that generally it will show normal spinel, but there are some cases where mixed spinel also can be seen. When CFSE of both dipositive and tripositive ions are 0, both are having CFSE 0 and the sizes are comparable. Okay, so size of the both the cations, tripositive cations and dipositive cation should be similar. Okay, so then it can, so some of the portion remains as normal and some can be inverse, because there are no differentiate, we can't differentiate between them. The CFSE is also 0 and the size matters, because for the lattice energy actually when it is in octahedral field, okay, when it is in tetrahedral field, so the in octahedral, when it is in octahedral void actually, the 3 for the case of 3 plus ions, actually the lattice energy is high. Okay, So that will be a differentiating case when the sizes are different. Okay, so the lattice energy uh, is a important thing for that cases. But here sizes are also comparable. That time, if these two conditions actually is there, that time some portion can remain as normal and some can be inverse. For example, Mn Fe2O4. Okay, so Mn is here 2 plus, which is D5, and CFS is 0, right? And Fe3 plus is D5 and CFS is 0. So in that cases both have CFS is 0, it will show some mixed final. It will have some portion as normal and as inverse. Okay. So for the case of mixed final, actually you can't define a mixed final. You can have an idea by these two conditions if in the questions given that it is mixed final or not. So in these two criteria you have a idea, but you have to remember few examples to to know about the what are the mixed finals. Okay, but I think when in the question it is given some mixed finals are given, well, that time these two criteria you can see actually. Okay, so you can solve and can find out, I think. Now the examples of mixed final, here also some examples are given. So M into Fe2O4 we have seen. I have also calculated both CFSs are 0. Okay. Now MgFe2O4, obviously for non-transition metal CFS is 0, right? And Fe3 plus has CFS is 0. So both criterias, okay, and the sizes are comparable. So both criterias are actually fulfilled, and these will show the mixed final. Okay, so these two examples you try to remember. Now the percentage of occupancy means, so we have told that for the normal spinal, okay, so for the normal spinal, A will be in tetrahedral, B will be in octahedral. Okay, so the percentage of occupancy, if in the question it is asked, then what we will do. Okay, so I have previously told you, if in the number of octahedral void, the number of atom in the lattice for a unit cell is it is, let's say, the n, that time the number of tetrahedral void will be the 2n, and the number of okay, so the number of octahedral void will be n, right? I have previously told you. Now how can we now calculate the occupancy? Let's say here I have told you for this kind of lattice, anions are actually forming lattice. It has the anion, 4 anions. So here n is equal to 4. So number of octahedral void is 4, and tetrahedral void is 8. Okay, so tetrahedral void is 8. Okay, so the here for the normal spinal, what is happening? A2 plus is in tetrahedral void, B3 plus is in octahedral void. So tetrahedral means 8. So here the one, let's say one atom we are considering, one ion A2 plus is in among the 8 tetrahedral voids. So the occupancy is 1 by 8, right? 1 by 8, because 1 is the number of ions there, and they can see it in 8 places. So the occupancy for each void, each tetrahedral void will be 1 by 8, right? And if we can calculate in the percentage, it will be into 100, which will be equal to 12.5%. Okay, and in the octahedral void, I have talked in the tetrahedral, the case of tetrahedral void, but in the octahedral void, same right? 4 number of octahedral voids are present, and the cations are 2, because 1:2 ratio is there maintained between A and B. So here occupancy will be for each void. So each void. So 3 plus cations are inside, are among the 4 octahedral voids. It can be sit anywhere between the 4, right? It can be exchanged between the 4 octahedral void also. So we don't know where it will sit. It will sit among 4. So how can we calculate the occupancy for each octahedral void? It will be 2 by 4, which is 1 by 2, and in the percentage it will be 100 multiplied by, and it is 50%. So if you are asked that for a normal spinal, or you have given an example and you have to find that out that it is normal or inverse, and the question are given like that way, that the percentage of occupancy for this crystal is in octahedral void and tetrahedral void. Okay, so you have to first find out that it is normal or inverse, then you have to calculate the percentage of occupancy. This is very simple. If you know that how many number of tetrahedral voids are there and octahedral voids are there, you can easily calculate. Okay, and now for the case of inverse spinal, what will happen? For the case of inverse spinal, we know that B3 plus, half of the B3 plus is in tetrahedral void, and A2 plus and B3 plus. Okay, these are in octahedral void and X4 is present. Okay, fine. So if let's say you are asked that the occupancy of the case of this inverse spinal, the occupancy of A2 plus ion, what will be the occupancy of A2 plus ion, let's say. Okay, what will be? So it is in now octahedral void, and octahedral void is 4. For the case of normal or inverse, the n is here 4, n is 4. So octahedral void is 4, tetrahedral void is 8. Okay, so occupancy of A2 plus is, it is 1. Number of A2 plus is 1, right? So 1 by 4 into 100, let's say, percentage occupancy, which will be 25%. Fine. Okay. Now occupancy of B3 plus in octahedral. Let's say you are asked that how much percentage of B3 plus actually occupied in the octahedral void. So you have to calculate like that way. You don't because you cannot say that one atom is occupied. You have to calculate in the percentage, right? Because crystals are having many atoms, can have many atoms, right? Because in 1 mole 6.22 6.022 into 10 to the power 23 number of atoms are there. So that is the case. So B3 plus in octahedral, now what? Octahedral 1, again 1 by 4 into 100, because another one is gone in tetrahedral. So here it will be again 25%. So occupancy of B3 plus in octahedral, and occupancy of B3 plus in tetrahedral will be what? So tetrahedral 1 by 8, right? 1, this B3 plus ion is occupying between 8 tetrahedral voids, right? So it will be this. It will be now the again 12.5, right? 12.5%. Okay, these are the percentage of occupancy. Now coming to the question. So this is coming in the GATE exam, the GATE 2008. So among the compounds Fe3O4, Ni, Fe2O4, Mn3O4, what are normal and what are inverse? Okay, some questions are some options are given here. So let's say first one, we have previously calculated it. It was inverse, right? You know now. And second one, Fe2O4, it has this Ni2 plus and Fe3 plus. So we have to calculate the Ni2 plus CFSE in octahedral. It is D8, right? And it has highest CFSE. How? So 1, 2, 3, 4, 5, 6, 7, 8. Okay. So point minus 0.4 into 6 plus 0.6 into 2. Okay. So minus 2.4 plus 1.2. It will be minus 1.2 Delo. Fine. Now for Fe3 plus. Fe3 plus, this is D5, right? This CFSE will be 0. So it will be what? Here CFSE of the dipositive cation in octahedral field is greater than the tripositive cation in the same condition. Okay, so it will be obviously inverse spinel. Inverse spinel. Okay, so NiFe2O4 is inverse. So this is wrong. Here it is written normal, and here it is not written. Here is this one. Fe3O4 and NiFe2O4 are inverse spinel. So we know NiFe2O4 is inverse spinel and Fe3O4 is obviously inverse. So D will be the correct option. So, but if you want to know that what kind of crystal it will make this Mn3O4, so it has Mn2 plus in tetrahedral. So the CFSE will be 0 for this because D5 system, and for Mn3 plus there will be non-zero CFSE. We will calculate it. So CFSE will not equal to 0. So it will be obviously normal spinel. Okay, it is normal. Some options are given. Actually, this is normal, but other thing is actually wrong. So it has both the things are correct. So it will be the correct option. Okay. The next one is for an inverse spinel. It is given that it is an inverse spinel. AB2O4. Okay. A and B are respectively what? So you have to see all the options and then find out. So let's say A is Ni2 plus. Okay. Okay, Ni2 plus, and it is gallium 2O4. Okay. So what is there? This can be inverse, right? Because it is a D8 system, and D8 systems are stable in octahedral. We have previously did it. So for the case of this, let's say Fe and Cr2O4. Okay. This has Cr3 plus, right? D3. It has highest CFSE. This has some CFSE, but it has highest CFSE. We have told that D3 and D8 should be in what? Octahedral field. So it will be normal spinal. Okay. Let's not talk about this. This is wrong. Okay. Now Zn2 and Fe3. So we know Zn2 is D10 and Fe3 is what? D5. Both have CFSE 0. It can be mixed spinal or normal spinal. Okay. No, not inverse. It is wrong. And last option is Mn, Mn3. Okay, Mn2 and Mn3 means Mn3O4, which I just now I have talked about this. This will be normal spinal, right? This will be normal spinal because Mn3 plus has some CFSE, but Mn2 plus is 0 CFSE. Okay. So what will be the answer? The answer is A. A is the correct answer. Okay. This one, because D8 it will prefer in the octahedral void, and gallium it doesn't have any CFSE. Okay. So obviously we can see that it will be the inverse spinal. See, this is also a GATE 2024 question. Okay. So I have shown you various examples. Okay. You can now practice a little bit, practice more to have the clear idea about it. But I hope you have understood the basic concept about it. You can solve the questions. Okay. But just practice it in a more practice actually can make the perfect answer. So you have to practice more. So see you in the next session. So thank you so much.